Let's talk about Minkowski's space and the Lorentz transformations, and also want to give a big thanks to Mark Z, who had a very good video. There was one place where I felt that he hand-waved a bit too much, and one place where he wrote an equation down incorrectly, but that error did not get propagated through because the next time he used that equation, he wrote it correctly. But this is my version of what he had done. So let's start talking about just point of view. In physics, we call that a reference frame. So we're going to take a look at the scenario. I have two objects, A and B, and if you like to think about it, A as being a person and B is a car moving to the right from our point of view. We'll go ahead and say B is traveling in the positive direction. So I'm going to establish that at time is equal to 0, position is equal to 0 along some sort of x-axis. And so when the car is right there, when the car is closest to the person, that is when we're setting time is equal to 0 and the position is equal to 0. So the car starts out to the left on the negative side of A and then moves to the right. And so B starts out on the negative side and then is even with the person and then keeps progressing in the positive direction. So as time is increasing, position is increasing. And then from B's point of view, B is sitting still and A is moving off that way. So we're establishing to the right is positive from B's point of view. And so we start out before time is equal to 0. In other words, before they are even with each other, that the person is on the positive side of the car, or on the positive, A is on the positive side of B. And as time progresses, they are even with each other, and then A moves into the negative space or negative position as time becomes positive. So both of these are perfectly valid points of view when dealing with physics, and we should be able to derive the exact same results no matter which point of view we're looking at. That's one of the tenets of physics, and which is basically stated right there. So now let's deal with a faster situation of something traveling at relativistic speeds. So something traveling near the speed of light. And using the graph suddenly becomes a lot more difficult because the time here, we can still use time and position, but 1 second is basically the equivalent of almost 300 million meters, whereas one on the horizontal scale would just be 1 meter. And so these become incredibly skewed. There are several ways of dealing with this, one of which is to just keep this scale and just have lines that really are almost indistinguishable from axes in a lot of cases. But traditionally, the way you deal with it is you take your position divided by the speed of light, and now this is in light seconds, and that is in seconds, or do c times d and keep that in meters and that in meters. This is the way I do it. I have seen it this way. And then there's a confusing way of dealing with it. I know there's a certain segment of the physics population which likes to do this. I'm not personally a fan, but I understand why they do it. It does simplify the equations. They use what are called natural units. In natural units, c is equal to 1. You can think about it this way: is there exists a unit system such as the speed of light is 1, and that's what they're choosing, in which case you have x and t. And the trouble with this is that if you're not using natural units, suddenly you have to shift. You have to then go through and figure out, oh, where the c is supposed to be. Now, the advantage of this is it does simplify equations. If you think about probably the most famous equation in physics of E equals mc squared, that equation now just becomes E equals m. And it can get confusing unless you are sort of versed in that speak. And again, not a fan. But I did experimental work and not theoretical work, so it made a difference where you stuck the C. So I'm going to be doing it this way. I'm still going to refer to this as the time axis, even though it technically is not time anymore. It's how far light travels within a certain amount of time. But on this axis right here, light would travel at a 45-degree angle, so that's a 45-degree angle right there. And that's also a 45-degree angle. And it really doesn't matter what reference frame you're in. Speed of light is going to be the same regardless of the reference frame. This was a result of several things leading up to Einstein's intellectual breakthrough. So in this scenario, again, I'll have an object A and object B. Object B is traveling at relativistic speeds. I had half the speed of light on the other page. And so I have, and I'm going to synchronize it so that time is equal to 0 when they are as close as possible to each other. And so we have it looking like this. I do have my 45-degree angle here of light. And so since B is traveling less than the speed of light, it will be traveling somewhere in between there at rest and there at the speed of light. So it'll be traveling somewhere in between. Or from B's point of view, A is traveling at relativistic speeds to the left, and its graph would look like something like that. So now let's deal with the scenario of A and B are sending signals back and forth to each other. So A sends a signal to B, B immediately reflects it back to A. And this is how you're going to synchronize the clocks initially, that at this point right here, when they're closest to each other, that the distance between them is so close to 0 that we're going to count it as 0. And so the signal that A sends, B reflects back immediately, and so that's how they synchronize the two clocks. A sends, B receives, B reflects, A receives, all at the same moment, or close enough for physics. After a set amount of time, A is then going to send a second signal. B will get it, reflect it back, and so we get these moments where how long does it take for B to receive the signal? How long does it take for B to send the signal? Likewise, how does that relate to the amount of time it takes for A to send the signal and A to receive the signal? This can be summed up a little bit better in the graph right here, that they synchronize, so the first signal is sent and the exchange is immediate. And then after some time, TS, a second signal is sent. It is sent along. Now B is no longer right there at A, and so it takes time for it to get there, at which point it is reflected back. From B's point of view, B is at rest and A is moving, and there's at some point when A sends a signal, B receives it and reflects it, and A gets it back. So we have these various times here of, I'm using S for send and R for receiving. So we have the time it takes for A to send the signal, so it sends it at this point, and then a certain amount of time later it sends a second signal. B, on the other hand, receives the signal at our origin here, and then it will receive a second signal at this point, at which point it sends the next signal. And so we have the time of B receiving, which will also be the time of B sending the second signal. And then A is going to receive it. And so we're going to now take a look at the relationship between these. And again, this is just stating what I just did, that the time it takes for B to receive a signal is the same as the amount of time it takes it to send a signal, just because it's an automatic reflection. Now, the distance that B travels in the amount of time it takes to receive it, so we'll just assume it's at some time T1 is when it actually receives it. And so it's traveled some distance D. This dotted line right here is at a 45-degree angle. So that's a 45-degree angle. That's a right angle, and so that's 45. And so I have a 45, 45, 90 triangle. In other words, this length right here and this length right here from here to here are the same. Therefore, this distance, the time it takes for A to send a signal, is just going to be equal to CT1 minus D. In other words, the distance that was traveled, which ultimately is going to be the speed of B times T1. Over here, when A receives the second signal, it is going to be CT1 plus D. So CT1 is this time right here, or technically this distance, plus this value of D, how far B has traveled. And so CTA receiving the second signal is CT1 plus D. Over here, what we care about is this point right here, the point of B receiving, and so the time it takes for B to send the second signal. Because again, the first signal was sent at this point. So we'll establish K to be the ratio of, in essence, the time it takes to receive it in the frame that's moving over the time it takes to send it in the frame that's not moving. So from A's point of view, A is at rest. And so the time it takes for it to send a signal is this time right here, or which I've labeled as CTAS. And the time it takes for in the moving frame to receive it is this distance right here, or CTBR. And so that ratio And there's no reason why there's a special reference frame from A's point of view or from B's point of view that you should be able to get the same physics out of it. And so if I look at the sending of signal from B to A, well, from B's point of view, B is at rest, and so the amount of time it takes to send that second signal is CTBS2. And A is receiving it, and so A is receiving over here is going to be that amount of time, which I've labeled as CTAR2. And again, I sort of talked about this already, but CTAS, in other words, this distance right here, is just CT1 minus this distance right here, which is VBT, which we'll get into a little bit later, VBT1, which we'll get into at some point. And then this over here would be CT1 plus D. So we're now dealing with this relationship right here. That's the first one that we did, that CTBR over CTAS is CTBR over CT1 minus D. Looking at the second one, we have K is equal to CTAR2 over CTBS2, and CTAR2 is just CT1 plus D, and CTBS2, as we'll show right here, is same as CTBR. So the time it takes for B to receive the second signal is the same amount of time it takes it to send the second signal. And so from this relationship right here, we have what CTBR is by just flopping these across the equal sign, and so we had CT1 plus D over K, and then we plug that into this equation over here. So plugging that into that first equation there, we get this multiplied by K, and so we get K squared is CT1 plus D over CT1 minus D. Now we bring in the fact that D is just how fast the rocket is traveling at some speed V times T1. I'm going to factor out CT1, and I'm left with 1 plus V over C on top and 1 minus V over C on the bottom, because these will cancel out. And remember that beta is the speed relative to the speed of light. It's just V over C, so this becomes 1 plus beta over 1 minus beta. And ultimately, we get this value of K is equal to the square root of 1 plus beta over 1 minus beta. And again, this if they're moving away from each other. And this is the relativistic Doppler factor. If you've there are other ways of deriving the Doppler factor, and I do that in another video, so just be aware. There are other ways of getting to the exact same place. So we have TR prime. Now I'm going to the more classic reference of prime being the moving frame. So TR prime is equal to TS times the square root of 1 plus beta over 1 minus beta. That's just plugging K in. We can put it in terms of frequency because period is 1 over the frequency, and we get this. So 1 over F prime R, 1 over Fs, take the reciprocal. And then if we want to do it in terms of wavelength, that the period is the wavelength divided by the speed of light. And so if you plug that in for T and then multiply by C, you get this relationship here. Now, this is if they're moving away. If they're moving towards each other, then you flip the sign, so this becomes a negative and that becomes a plus, or plus minus, or minus plus. And so oftentimes it'll just be written this way, where you've got the signs of plus, minus, minus, plus. And so the plus and the minus, top two signs go together, or the bottom two signs go together, and you just have to think through, oh, is my frequency going to increase or decrease? And that's usually the way it's done. And oftentimes that the prime is taken away and you're just supposed to know. So now let's take a look at the following scenario, that there's some event that happens. So from A's point of view, A is, let's just say it's Earth, and there's some planet M that B is going towards, and M explodes at some point along the journey. So from Earth's point of view, M basically stays in the exact same place at all times, and B is traveling towards it. So if B explodes at some point along the journey, then it's going to happen at a different position and time for A than it will be for B. So from B's point of view, M is traveling towards it and Earth is traveling away. At some point, M explodes. We need some sort of event. But we still have A sending a signal and B receiving a signal. Now the ratios we talked about before, Now before we had the time of B receiving is equal to the same as B sending. That is different in this scenario. So the ratio though of sending to receiving should still be the same. That doesn't change because I can always set up a different signal being sent and reflected. But the ratio of CT prime minus X prime over CT minus X should still be equal to CT plus X over CT prime plus X prime. Now I'll sort of define a few things here. X prime is the distance from M to B at the moment of the event. And since if that distance there is X prime, because again, that's how far away M is when the event occurs, from B's point of view, and light's traveling at a 45-degree angle in my graph here. And so this distance here has to be X. And so this is X prime. And so this is CT prime minus X prime, and this would be CT prime plus X prime because that and that and that are all the same length. And over here, CT, this happens at some time t. This would be CT right here. This would be CT minus X because this distance here is X. So CT minus X, CT plus X. So now, using the equation that we just derived, that the receiving in the moving frame, so from A's point of view, that is B is in the moving frame, so that would be CT R prime, and divided by the time of sending in the rest frame, so A's point of view, this is the rest frame being sent, so CT minus X. And so we have CT prime minus X prime is equal to K CT minus X, and I'm going to call that equation 1, and again, this is assuming A is at rest. Now, from B's point of view, for the signal sent from B to A, we have this distance from here to here, which is CT prime plus X prime, and then it's received at CT plus X. So this is the receiving is equal to K times the sending, and we call that equation 2, and that's sort of B is at rest in that scenario. So now it's a matter of just working through the math. We have CT prime minus X prime over is equal to KCT minus KX, so just distributing K here. Then multiply through by negative K to get this. And then I take my equation 2, just distribute the K, and then put this side first and then that side, so basically flipping this across the equal sign. And so I get KCT prime plus KX prime is equal to CT plus X. This is from equation 2. And then I add the two equations. Again, or the reason I multiplied by the negative here is so that those terms would cancel out. And I'm left with this plus this, which is 2kx prime is equal to that plus that. And then I'm going to factor them. Then using the commutative property of addition, I'm just going to rearrange the order, and then I'm going to factor out CT. So these terms have CT in it, so I'll factor CT out, and I'm left with a 1 minus k squared. And the other one I have an x in common, so I'll factor x out, and I'll have to 1 plus k squared. So now I can come up with a relationship between x prime and x and t by dividing by 2k. Now we have this minus sign suddenly seemingly to appear, but that's because I flipped this order around here. I could have kept it at 1 minus k squared, but it's just convenient, in my opinion, to make it k squared minus 1. And so I take my 1 minus k squared, factor a negative 1 out to get k squared minus 1 with a negative there. I do very similar to what I do over here, except this time instead of multiplying by negative k, I multiply by k. And this time the second term is going to cancel out on the left side, and I'm left with 2kct prime is equal to that. Then I divide by 2kc. The c cancels out here, and over here I'm left still with the c on the bottom, and then I have the 2k. And again, I flipped that around and brought out a minus sign. So that's equation 4 and 6, and we will use those in just a moment. Reminder of what k is. This is what we derived earlier in the video. And then we'd plug in. So I'm taking my first bit here. I wrote it as k squared plus 1 on the other page instead of 1 plus k squared, but hopefully you can deal with that difference in math. So 1 plus k squared over 2k, plugging in the value for k, or the formula for k, I get this. I get a common denominator on top, and on the bottom I just sort of break my radical up into one radical divided by another. Because basically I'm trying to set this up as a single fraction in the denominator. So on top, my betas cancel out. I'm left with 2 over 1 minus beta, and then dividing by this fraction, same as multiplying by the reciprocal. 2's cancel out. And then the other bit of math here is I have the square root of 1 minus beta over 1 minus beta. A couple ways of looking at it. So 1 minus beta to the 1/2 over 1 minus beta to the 1, which is 1 minus beta to the negative 1/2. And so that's why we have a square root of 1 minus beta on the bottom here. When I multiply these two radicals together, I get the radical of 1 minus beta squared. And 1 over that, as we have, is just the Lorentz factor gamma. That is equation 7. We go through a similar process for the other coefficient, k squared minus 1 over 2k. I make the substitution for k, get a common denominator in this part right here. This time the 1's cancel out, and I'm left with 2 beta on top and 1 minus beta on the bottom, and then flip this fraction around when I multiply. The 2's cancel out, and I'm left with beta times 1 over the square root of 1 minus beta squared, or beta times gamma. I will take those two values for my coefficients, plug them into equations 4 and 6, and so I have x prime is equal to gamma x minus beta gamma ct. Factor out the gamma, and then beta times c is just the speed, so vt. So I'm left with x prime is equal to gamma x minus vt. Very similar over here where I have t prime is equal to gamma t minus beta gamma over xc. Gamma t minus beta gamma x over c, which gets me factoring out a gamma. I get this, and then using that relationship that beta is v over c, I get gamma times t minus vx over c squared, and these are the two Lorentz transformations. And then we can always flip the point of view and come up with the value of x in terms of x prime, or t in terms of t prime, which looks very similar to this, but that's in another video. Don't need to derive that piece of it, but thus it is shown. Now let's take that last step of how do we look at this a little bit differently. And this is how we look at it a little bit differently. I have some event that happens. Well, if we think about it, if I've got a normal perpendicular axes here, and this is position and time, well, if I want to figure out what is the position here, I go parallel to my time axis, and that tells me my position. If I want to figure out what the time is, I go parallel to my position axis, and that tells me the time. Well, in essence, what we're dealing with here is a changing of my axes. If I've got, from A's point of view, A is sitting still and it's got the perpendicular axes, but B is not. B is basically taking my axes and it is shifting them. So this would be the position axis, and there's also a time axis which moves at the same angle. That angle and that angle are the same. And so this is my x prime axis and my t prime axis. And so if I have an event that happens here, so at time is equal to 0 at some distance away, well, if my axes change for B's point of view, well, let's think about that. If I want to figure out the position in B's frame, I just go parallel to its time axis, because my time axis is now at an angle. Go parallel to that, and that tells me position. There's my x prime. If I want to figure out my time, I go parallel to my x prime axis, and that tells me the time. So this event that happens at time is equal to 0, from A's point of view, happens in the past from B's point of view. So if in the scenario we had before where B is a rocket shooting off and passing by A, and this is the point in which it passes it, the event happens before B gets to A, and the position is obviously also different. This gets into the idea of simultaneity, but a different way of looking at it, and there it is.